Welcome to Industrial PLC Applications. This video is a closer look at the Micro850 PLC trainer. In this video, we'll be looking closely at the Micro850 PLC installed in the trainer unit. We'll review the key components and some of the wiring methods used that impact operation. When working with Connected Components Workbench, you will see a graphic representation of the PLC you are programming. However, it does not resemble the unit installed in the trainer. The trainer has additional modules installed, and these are not in our project. We will show you how to do that in another video. Alright, so let's start this logically. We'll start with the power supply. The 120 volt AC to 24 volt DC power supply supplies power to both the PLC CPU module and also the I/O. Power to the CPU is made through a backplane connection. Power to the I/O is done using two positive and negative 24 volt DC power taps on the bottom of the power supply. There is a power LED to indicate power is present. The power supply also has some built-in I/O load overcurrent protection. To the right of the power supply is the actual CPU module. The PLC CPU module handles all I/O scanning, network connections, self-diagnostics, and the program logic. The CPU runs the logic by scanning the inputs, solving the logic, setting the outputs, and then performing some housekeeping, and then repeat. The center face has three different communication ports: Ethernet, DF1 serial, and USB. When you're trying to go online with the PLC, check that the two Ethernet LEDs are active. No activity, check the connections and power. On the right side of the center module, there are three LED sections. The top one are inputs, the middle section is for status, and the bottom is the outputs. Through some of these LEDs quickly. The first block are the input LEDs. These indicate the status of the input. It's lit when the input is receiving a signal and is off when they aren't. If an input doesn't trigger a response, check the LED and then check the wiring. If the LED is lit and you're not getting the desired result, it's likely your logic or a situation where something is being forced on. The next two LEDs, MS and NS, are network related, with the MS being module status. Basically, green is good, red is a problem. The Ethernet LED is similar, but if it's steady red, then there's a conflict with a duplicate IP address. And therefore, with that, it's been detected and the module will not connect. With both these LEDs, if it's flashing red and green, it means it's performing a self-test. Now we'll go to the status LEDs in the center. So we have the power LED, and this says that there's power coming from the power supply. This LED should always agree with the power supply's LED. If it is off, it could be a couple of things, but the first thing to do is to shut off the power to the power supply and then check to see if the CPU module is properly seated. There's a snapping latch mechanism that does that, but if the person installing it wasn't paying attention and didn't actually snap it, machine vibration, all the rest of it, it might work itself loose. If that's the case, if once it's properly seated, reconnect the power supply and restore power. If the two still do not agree, the two LEDs don't agree, then the power supply's output voltage might be suspect. It might not be sufficient. You should check it and replace if necessary. The run LED is lit when the PLC is executing the logic. Don't forget we have the mode of also being in program mode. The difference between run mode and program mode is that program mode, you're not executing the logic. Once you go to program mode, all of the outputs are turned off, and the inputs they'll still be made because of them being a syncing, so they'll still be lit, but they're not going to impact the PLC. They won't scan them and won't activate them. When you go to run mode, that's when the outputs will be energized. The PLC fault LED is lit when there's a critical PLC fault. Try to connect to the PLC and see if there's any fault information shown in Connected Components Workbench and take action. Normally, the software will prevent you from writing logic that will cause the PLC to have a suicidal fault. In other words, it's one that you've created. So the build process stops that. One of the faults that used to occur with PLCs is putting a negative time base in a timer. We can't go back in time, and neither can the PLC, so having a negative time would be a major fault. However, I did an experiment where I was moving variables and subtracting a time to slow something down, and the value actually got to be negative because I didn't put a check. And the PLC said, oh, that's not a valid number, and would not execute it, but it did not create a fault. I did not see a fault come up on the simulator, which is interesting. Okay, if you do have a fault, there is a way you can attempt to clear it. So down on the bottom, there is the remote, the run remote program toggle switch, and that's below that Ethernet or USB, port. It's a very tiny little switch. So all you basically do is move the switch to program, and then move it all the way to run, and then move it all the way back to program. And if you've done that twice type thing and the fault doesn't clear, yeah, it's a major fault. You're going to have to get online, hope to find a fault code, and take major action. You might even have to replace the PLC unit itself. Now, normally what will happen if you do that twice, the fault light should clear, and then you can move it to remote or to run, depending on what you want to do. If you move it to remote, you're going to have to put it in run mode through the Connected Component Workbench. If you put it into run all the way and then move it back to remote, it will already start executing the program. The last LED on this block is the COM LED. Now that one's lit when you're using the RS-232 communication activity. On the bottom block are the output LEDs. They basically tell you the status of the LED, whether it's on or off. Now this is normally by the program, but it will also be indicated if an output has been forced on through the forcing mechanism. On the very bottom of the CPU module is a tiny 3-position switch. The 3 positions are run, remote, and program. Leave it in the middle remote position. The next 3 modules are chassis modules. Chassis modules are modules that are inserted into the backplane of the chassis. Chassis modules are not plug and play. That is, the PLC will not even pull them until they are added to the project. These modules will receive power to their electronics via the backplane, and they have their own specific wiring terminal blocks. The first 2 modules are analog modules, that is the 2080 IF2 and the 2080 OF2. These work with varying voltage or current signals as opposed to digital or discrete modules, which only work with 1s and 0s. The third module is an isolated relay module. The 2080 IF2 analog input module has 2 channels that can receive analog signals from 2 different devices like transmitters. The PLC can then apply that data to the logic. The 2080 OF2 is an analog output module, and it too has two channels that sends two different analog signals out. This allows the PLC to control an analog output like motorized gate valve, etc. The 2080 OW4 module is an isolated relay module. It has 4 electronic relays which open or close their own independent set of dry contacts. For a complete explanation as to what isolation relays do, please see the video. The last module is a piggyback daughter module in that it is added to the backplane bus rather than through the 3 fixed channel chassis slots. It is an IRT4 module, which is used to read temperature into the PLC. This device has 2 RTD channels and 1 thermocouple channel, complete with its own thermistor. This module receives raw, analog, thermocouple, temperature, and RTD measurements. The module needs to be configured before use. Recall, the thermocouples are active devices, producing small voltages based on temperature variations, but RTDs are passive devices where the resistance changes based on temperature exposure. Therefore, the inputs are not interchangeable. Anytime you're dealing with an Allen Bradley PLC, especially with the Micro 800 family, you need to know the part number. It's a good starting point. There'll be variations depending on modules installed, etc., but you need to know the proper part number. So this particular model we're using, its model number is on the top. It's a 2080 LC50 24QBB. You'll be needing this every time you create a project. Right below it is the MAC ID number. This number is used by Ethernet devices and is contained within the packet. It can't be changed. It's that number that's firmware installed in the Ethernet device itself. On the top of the chassis is the connection and termination point for the inputs. The 14 fixed inputs are connected to the power supply's power taps. The input terminal strip is supplied by 2 different 24-volt DC positive common connections. So you have COM0, as you can see on the bottom left-hand corner, supplies the inputs from input 0 through 7, and COM1 supplies inputs 8 through 13. The fixed inputs themselves are called syncing inputs. So the 14 inputs used on this Micro 800 are syncing inputs. Syncing means that the power goes out to the input device and only triggers a PLC input when the power goes through a closed input. It's syncing the voltage at the input terminal that gives us this method's name. The 10 fixed outputs are connected to the power supply's power taps as well. The output terminal strip is supplied by 3 24-volt positive and negative commons. One pair supplies the chassis backplane. The second pair supplies outputs 0 and 1, and the final pair supplies the output 2 through 9. Fixed outputs are sourcing outputs. The outputs on a Micro 800 are sourcing. This means that the source of power for the external devices comes from the PLC. The PLC is the source. So power goes through a common power rail, and the outputs internally are basically switches, and when the output is energized, the switch is closed and the external device is turned on. Since the power is coming from the PLC's 24-volt DC power supply, it makes sense there is a limit to the amount of current the output devices can draw before exceeding the power supply's output. In these cases, it will be necessary to have those loads with their own power source and only signal them to energize. You may notice that most of the wiring used is the same color for supply and inputs and output loads. This was not the case at my previous employer. Wire colors indicated different things. The point here is never assume that all places or companies apply the same methods and/or color schemes. As part of being a good electrician, working safely also means no assumptions and reading the prints. In order to connect with external devices, the trainer has an assortment of input and output terminals duplicated and connected to jack ports. There are 4 input and output jack ports, a set of RTD jack ports and thermocouple jack ports, and a set of analog input and output jack ports. Another video will go over their correct wiring and application. On top of the trainer you'll find the connection cluster. 120 volt power is connected to the trainer via the standard male 3-pin power connector. If the unit does not power up, check the built-in 3 amp circuit breaker. The other 3 connections are an external Ethernet port, a USB connection, and a RS-232 9-pin serial connection. If they do not initially work, check that they are still connected inside the trainer. Note, the USB connection is plug and play. If the USB port does not show up during a connection attempt and the internal jumper cable is correctly installed, then it is likely a Windows update has overwritten the PNP driver and the program will need to be reinstalled. There you have it, the complete tour of the internal workings of our trainer. Please stay tuned for more videos, including the video